Hello everyone. Today I will talk about the latest reasoning models that have become the talk of the town in the last 1 month, uh, which is the DeepSeek R1 models. Uh, and not just DeepSeek R1, but that has resulted in a flurry of activity, a lot of open source projects that have been inspired by DeepSeek R1. So we will talk about all of them. So, what is DeepSeek R1 and where do we place it in the scheme of things? So, DeepSeek R1 is a reasoning model and it's one more step in the evolution of language models that we have seen since the rise of deep learning. So, if you would trace the trajectory over the last 1 decade or so, we started with word embeddings where we could capture semantic similarities between words but couldn't really capture contextual meaning. Then we came to natural language understanding application models, uh, which are encoder models like BERT, which could understand uh, contextual relationships, and therefore uh, they could be used for many natural language applications by fine tuning the models for specific tasks. The models were of course pre-trained on a lot of data, which gave them a lot of inbuilt knowledge. Uh, Encoded models could still only do uh, understanding. So the next set of models that came were generation models in the form of encoder decoder models, where you had two separate components: the input text being processed by the encoder and understanding the input, whereas the decoder was responsible for generation of the text. So these models enable generation, but this generation was sort of conditioned on some input text. So these were not purely what you would call generative models, uh, but they could condition to generate text based on an input. And the class of models, with examples of some of the models in this class are P5 and BART. Okay, and all these models, encoder models, they really got a boost with the rise of the transformer architecture, which powers all the language models and particularly the large language models, which we'll come to next. So the next layer of evolution was the decoder only models, which are basically the fundamental architecture for all the large language models today. So these are models that only have a decoder. So they're just trained on a next word prediction task, a standard causal modeling task, and by training on a large amount of compute and a large amount of data, these decoder only models kind of learn interesting capabilities. And this was first exemplified by the GPT-3 model. Uh, and it showed that, okay, even without any task specific training that you had to do in the previous set of pre-trained models, the model could have interesting ability to learn by just looking at a few examples, which is called in context learning. Now, uh, from there, the next step was RLHF, which is these decoder models, which are, as I said, just trained on the next word prediction task. It's a very simple objective, but how do you make it useful for end tasks? So here, this step sort of involves post-training these pre-trained models on supervised data and more importantly on human feedback with reinforcement learning, so that the model conforms to certain values, uh, certain and can make decisions about preferences, etc. Right? And this sort of was a revolution. I mean, in the late December 2022, when ChatGPT 2023 ChatGPT came about, this sort of caused a revolution and sparked the latest interest in GPT, in large language models and AI. And we've seen a lot of enhancements on this basic framework over the last couple of years, particularly a lot of activity on the post-training side as well as on the pre-training side in terms of model scale up, the data scale up, etc. But now a new capability has come up, which has received a lot of attention in the last few months, particularly with OpenAI releasing its O1 series of models. So these are models with reasoning capabilities. So these are models that, given a input prompt, thinks and then generates output. So thinking means it sort of has a chain of thought kind of process. It generates output tokens, takes time, and then generates the output. Now, when it comes to reasoning capabilities, there are a few uh, details, there are a few components that these models have. So one strategy that is particularly effective is test time compute scaling, which is to give the model more time to think at inference time and have more uh, better inference strategies, so that the model can look at different alternative solutions, score them, and then search amongst possible alternatives and take more time to give more better uh, outputs. Right? So this is one thing that the O1 series of models are most likely doing. And to aid this kind of test time scaling, uh, reward models have evolved. So traditionally, reward models have been outcome reward models, which means that when you're doing reinforcement learning, you get the reward after the entire sequence has been generated. Then that's when the reward is computed. Those reward models give rewards every step, and because now you can uh, compute rewards for every step, uh, that helps test time compute scaling, because now you can score candidates intelligently and navigate a complex search space to find good candidates. Uh, the one of the most complex ones is the third one, which is pure reinforcement learning. So here, this is not at inference time, but at training time, the model kind of automatically learning reasoning capabilities uh, via uh, just being given rewards. So you have the prompt, and then uh, rewards are given during training time, which I'll come to later. And this very simple process enables the model to come up with reasoning behavior without any explicit uh, training. So, and this is what DeepSeek R1 is doing. Those series models also might be doing it. We don't know, but they also do test time compute scaling. So all these capabilities have resulted in a lot of reasoning models coming out, and now almost all models that are coming out are coming with reasoning capabilities, or at least, if not, uh, everybody is benchmarking on reasoning tasks, which kind of is the next frontier supposedly for the large language models in terms of the kind of problems that they can tackle. So with that introduction, let's dig deeper. Uh, so where do we put this class of reasoning models? So in terms of training an LLM and where they're placed, right? So these models typically you would place it in the post-training stage, where you are specializing the model for certain tasks. So reasoning is one kind of specialization. You have, for example, models specialized for uh, RAGs, models specialized for coding, for agents, etc. And reasoning models are one of them. But a very fundamental ability, which can also spill over and be useful for other kinds of specializations. Okay. So moving ahead. So now, what does a reasoning model look like? Okay, so here is an example from uh, this is an output from O3 Mini. So when you ask the model a question like what is why is 31 a prime number? Okay. Then the model sort of first takes time to reason about the solution. And that's called the thinking stage of the model. Once the thinking is done and it has an answer, then comes the answering stage, which typically is divided in two stages. There is an explanation stage where the answer is explained for interpretability and for any other use case, along with the final answer in the final answer stage. So, and the key idea behind the reasoning models is that more thinking time leads to better answers, and the more the model can think, do reasoning, do this chain of thoughts, the better it gets. This is another example from the DeepSeek R1 model. This is a question on geometry, distance between 2 points. And you can see that the model does a very detailed self dialogue compared to O3 Mini. Uh, it sort of answers, backtracks, uh, verifies, etc., etc., and finally comes up with the answer. And so that's the reasoning capability that these models possess. Now, the question is, okay, when should we use such reasoning models? Should I always use it or not? So this is kind of a nice summary of the key strengths and weaknesses of reasoning models. So they're good at deductive or inductive reasoning. So tasks that require reasoning like maths or coding or very in some domains complex reasoning, you should consider using reasoning models. The problems can be broken down into multiple steps. Use it, and for sort of better generalization to novel problems, which has not been seen in training data, but could possibly have been learned by reinforcement learning. Uh, when what are not good use cases for reasoning models? So one, uh, like if you want fast and cheap response is not good in many cases, especially when you have test time scaling, because you spend more time generating the thinking tokens. Um, and if you have to search multiple search paths, that's even more time. Uh, Now, sometimes the tasks are knowledge based, and in this case, the model can, in many cases, answer it out of the box. You don't really need reasoning, and reasoning might actually make it worse and lead to hallucination. And there are many simple tasks where you don't need very complex reasoning, but the model just goes on and on thinking. So for example, if you can try translation with R1 and it goes on doing very complex reasoning about doing word by word translation, etc., and then making a lot of arguments about how do I put the word structure and so on, and probably not required for a task like translation. So that's a case where you probably don't want to use reasoning. Okay, now coming to the topic of the day, which is DeepSeek. So DeepSeek, as we saw, is one of these reasoning models, and not just one. It stands out because it's the probably the first open weight state-of-the-art reasoning model that is competitive with OpenAI's O1 models. Uh, that's DeepSeek R1. But DeepSeek R1 is not the only model that DeepSeek came up with. In late December, they released DeepSeek V3, which is a base or a standard pre-trained plus instruction tuned model. This is an open source frontier LLM. Uh, and what stands out here is that they trained it very efficiently at a cheap cost and suboptimal hardware, which also got a lot of news and uh, raised a lot of attention. So it's these two models that, because of the efficiency gains, because of the state-of-the-art performance, uh, and because of the fact that they're open weight and that they have documented the methods, have brought about a lot of interest across the globe and let the community know about how do you build uh, models at scale efficiently and with high quality. And now there is a lot of effort to kind of replicate what DeepSeek has done, which we will talk about later after we first talk about DeepSeek. So before we delve into DeepSeek R1, let's look at DeepSeek V3, which is the frontier model, the base model on top of which R1 is fine-tuned. So DeepSeek V3 is a large model, 671 billion parameters. It's a mixture of experts model, uh, which means that at inference time, not all of its parameters are activated. And in fact, only 37 billion active parameters at inference time. It's trained on a lot of data, 15 trillion tokens. This is of the same order of magnitude as, say, Llama 3 has been trained. But it's been trained on much lesser compute uh, than all the other frontier models. Supposedly on about 2000 GPUs for 2 months, and so the sort of training cost run comes to around $6 million by some estimate, which is very cheap. Now, how did they achieve it? And that's some interesting uh, set of techniques they have used, which is talked about in the DeepSeek V3 report. Uh, One of the interesting things being FP8 training, and typically we do FP16 training. In this case, the team sort of uh, did a detailed analysis identifying parts of the network which can be substituted, where FP16 can be substituted by FP8 training, and along with a lot of other improvements on improved quantization, multi-head latent attention, auxiliary loss-free, load balancing, uh, optimizations for NOE, multi-token predictions. All of these adding up to a lot of efficiency, and some of these parts are actually now being open source. This week, DeepSeek is having an open source week, so they have released a few of these components for use by the community. And if you look at the results, DeepSeek V3 is competitive with any of the frontier models, GPT-4o, Llama 405 billion, Quen, etc. So that's the basis on which DeepSeek R1 is built. DeepSeek V3 is also interesting because it's a strong model and it's a lot of efficiency uh, gains. So now let's look at DeepSeek R1, which is a reasoning model. Now it's on par with OpenAI's O1 model, which at that time was the best model publicly available from OpenAI. Uh, but it's not closed, it's open weights, and there's a technical report with enough details to give an idea of what has been done and you could make an effort to replicate it. Not just DeepSeek R1, but it's MIT license, so you're free to distill and commercialize it. In fact, DeepSeek itself has distilled the R1 models into a set of Llama and Quen-based models, which is available publicly. They open source some of the innovations that power the efficient implementation that they have done. Their thinking tokens are visible when OpenAI first put out its O series models. The thinking tokens were not visible; they were hidden. But post R1's release, now for O3 Mini, even OpenAI is showing its thinking tokens. Um, and of course, then the website and API are available. The API costs are also significantly cheaper than other competitors. And the performance on benchmarks is very strong as well. On a lot of reasoning benchmarks like math problems like IME 2024, which is challenging maths data set, code forces, sweep bench verified, which are coding benchmarks, GPQ Diamond, which is STEM related benchmark, very challenging. So what does the DeepSeek R1 release provide? So it provides the R1 zero model, and this is the intermediate model that DeepSeek trained, and we'll talk about that, and R1. Now, R1 is a huge model, so it will require about 16 H100 GPUs via LLM to kind of load and infer. I said it's a 671 billion model, and they provided the distilled models, website, API, etc. Now let's delve into the details of how DeepSeek R1 was trained. This is the core of what we'll talk about today. So they have a multi-stage training pipeline, uh, uh, and let's go step by step. So the first step is what infuses reasoning, and this is the most important step of the entire process. Uh, the core reasoning is learned here. The rest of the stages are for some auxiliary uh, things. So what is done here is we start with the DeepSeek V3 base model and then do pure reinforcement learning on it. Uh, and this infuses reasoning and makes the model able to think about problems. Note that this is uh, no supervised data or supervised fine tuning is done here. It's just on the base model. The model that comes out of this process is what we call DeepSeek R10. Now, once this model is there, then the rest of the stages are done. And the reason you need the remaining stages is the R10 model is not the thinking process is not very readable. There are other issues. And so, in order to sort of make the model more consistent, more readable, uh, then they do the next stage where they do now this generate using the DeepSeek R10 model synthetic data consisting of the prompt, the reasoning trace, and the output. And this data is used for doing supervised fine tuning on the base model, the DeepSeek V3 base model. And now this gives us good starting initial point for doing reinforcement learning again. And why is this a good point? Because during synthetic data generation, care has been taken to include only those examples which have clean, correct reasoning traces. Now, once we have this SFT model ready, uh, you see that this is more readable, and with this model, we do the reinforcement learning process again. It's the same reinforcement learning process as in the first stage, but the only difference is that now we start with an SFT model, and this process now makes the model good at reasoning. It already was, but now it has also better readability and better language consistency, while being able to consistently output in a single language, which was a problem with the R10 model. Now, once this is done, now you have a very strong reasoning model, which is also readable and good to use. But this model is not as good on the variety of tasks that we use LLMs for. So you might use it for, say, coding abilities, for writing essays, for asking questions, etc. So the next step is to add these general capabilities, and so for this, this is like a standard post-training step. You do the SFT on the base model on a diverse data set. In this case, they use the same diverse data set that they use for post-training the DSV3 model. And along with that, they add all the reinforcement learning data as well in a final reinforcement learning stage. So now in this reinforcement learning stage, you do the standard alignment, reinforcement learning for alignment, as well as reinforcement learning for reasoning. And with that, you have a final model which supports all scenarios: reasoning, non-reasoning, making sure that the output is aligned, is readable, etc. And so that's the final DeepSeek R1 model that has been made publicly available. So let's go into each of these steps in detail, starting with the first model, which is the reinforcement learning on the base model, which kickstarts learning. As I said, this is the most important step. And here, what you're doing is large scale pure reinforcement learning on the base model. So no SFT, just take the base model. And the idea is to sort of infuse reasoning capabilities into the model. And as a, no so no supervised data means no reasoning traces. Okay, so all that the model is given, and as you can see from the uh, diagram below, a training prompt, in this case a coding question, and then there is a verifier which can verify any answer that the model generates. Right? So during training, the model kind of generates multiple possible solutions during reinforcement learning, samples out these multiple possible solutions, and these are scored by this reward function and that's the basis of the model improving the performance and learning to reason. Now, there is a very simple template during training, which just asks the model to do step-by-step thinking and output the answer and the thinking process in a certain format. Right? So that's the only thing, right? So the reasoning part makes the model, the reasoning prompt makes the model to reason, and then it gets better during training on reasoning, and which is driven by the reward function, which looks at the accuracy. But then there are also other rewards like the format reward, which makes sure that the output is generated in the correct format with the correct tags, etc. So it's a combination of things, but yeah, the accuracy reward is the most important reward that drives the learning process. So what we see after this reinforcement learning process is that the model automatically learns to think more. Okay? So if you look at its training plots, so as the number of steps increases, you can see that the model's thinking time, the number of tokens it generates is increasing. Right? And that's interesting. Uh, uh, yeah, no supervision, model just figured out based on reinforcement learning that it needs to think more to solve certain problems, and eventually its thinking time increased during training. And as the thinking time increases, you can see that the accuracy of the model also increases. So more thinking time leads to more better quality uh, translations. Sorry, better quality outputs. Okay. And with this, if you evaluate the model on certain tasks, many tasks, the model is already at par or pretty close to what say OpenAI's over models are doing. So the reasoning step already has learned quite a lot. The drawback, as I said, is it's the readability is poor of the thinking chains, and there is language mixing that often happens. The output is sort of a mix of English and maybe Chinese and the other languages, which is problematic. So, uh, one key thing to point out, which the paper also points out, is that the model sort of automatically learns to reevaluate its previous steps to explore alternative directions. And this is one chart from the paper that you can see on the right, which shows that uh, the model at a certain point during its reasoning process says, okay, wait, this is an aha moment that I can flag, and then it goes on to reevaluate, right? So it's sort of like the model is thinking like a human, speaking like a human, and uh, doing reflecting on its solution, and that's what they call the aha moment, which is very interesting. But now let's move to the next stage where now we still have to resolve the issues of readability and language mixing, and that's where this whole idea of uh, cold start from SFT takes shape. Now here what you do is to improve the readability and for better initialization for general performance, they use the R10 model to generate uh, long chain of thought data, but then do a lot of filtering to ensure, and along with some human verification to ensure that you can create a subset of data which is very high quality and use that to do SFT on the DSV3 base model again. Now, after SFT, cold start, now we do reinforcement learning on this cold start SFT model again, the same reasoning as in step one. So you have accuracy rewards, which is the main objective. You also have format rewards to ensure that the format is correct, and you also have language consistency reward, which is added at this stage to ensure that the output is consistently in one language. And with all this training, you come up with a good reasoning model. Then they do the SFT to introduce general capabilities. For this, a training data set of around 800K examples is created, 600K of reasoning and 800K of other capabilities from the DeepSeek V3 pipeline. That's where the 200K comes from. Whereas the reasoning data is, of course, coming from the model in the previous stage, plus rejection sampling and filtering for high quality data. And SFT is done for 2 epochs and followed by a final reinforcement learning for all scenarios. So here the model is trained to align to human preferences to improve helpfulness and harmlessness, as is done for all models these days after pre-training. And so in this case, there is both RL data as well as non-RL data. So for non-RL data, the data comes from human preferences, whereas for reasoning data, it's the rule-based verification that has been used the previous stages as well. So if you look at the benchmarks, so we can see that this final model is pretty strong across a range of benchmarks and even improves upon the DeepSeek R10 on many tasks. So this is kind of a very strong, powerful model. The next thing that DeepSeek has done is to distill these models, the R1 model, into smaller models, right? Because it might not always be possible to run these models. Uh, Running on a server has costs. Deploying the R1 model locally is not easy, but Can we have a smaller model which achieves the same capability? So that's the attempt. Uh, so these digital models have been generated by taking the same 800K training data for the final post training and generating their reasoning traces, outputs, possibly filtering out uh, wrong generations, wrong responses, uh, and then fine tuning one of the base models ranging from Quen 1.5 billion parameters to Quen 32, Llama 8 billion, Llama 70 billion for the Llama 3 series. Uh, and that simple supervised fine tuning is already fairly strong. It can beat many of the other uh, open source reasoning models available and is uh, maybe at the times competitive with even the large models. Okay, but yeah, there is still a decent gap between these digital models and the frontier models, the DeepSeek R1 model, as well as GPT-3 and all, and some of the tasks. So that gap still remains. So how do we do better reasoning with smaller models? That's an open question. How do we do better distillation? So fairly open. The question then might be, okay, should I do distillation with a small model? When I have a small model, should I distill from R1 or should I do pure reinforcement learning on a small model? And that's one ablation study that the team did, and it turns out that uh, distillation of large strong base models yields significantly uh, better results than reinforcement learning on a weaker base model, a smaller base model. And that sort of gives you some insights as to why R1 is doing so well with pure reinforcement learning. So it's not that pure reinforcement learning is something that people have not known, but it's not been applied successfully uh, in this kind of general setting uh, earlier. And what has enabled DeepSeek R1 to work? So it's probably the better base models that are needed for the RL process to find an interesting solution. Right? So if your base models are not good and reinforcement learning uh, just cannot reach solutions for certain problems, then the process will not proceed. And having better base models retain a lot of data, a lot of synthetic data, a lot of them might have seen chain of thought uh, data as well in their pre-training stage. Uh, Helps the model do reinforcement learning and reasoning chains better. So those are kind of the reasons why pure RL is now working, and also why that's probably not easy to do with smaller models. So to summarize, the key takeaways from the DeepSeek R1 work are that yeah, it's not important to start with a SFT model. You can still do pure RL. In fact, there are some studies which show that it might just be somewhat detrimental also. And complex reasoning behavior emerges from pure RL. We saw the examples of the model's ability to backtrack, to rethink, etc. But to that end, what is important is to have a high quality, a large base model, and distillation, as we saw, on a large RL model better than RL on a small model. Long context is also important because the model, you can see that the thinking chains are very long, and the model needs that kind of a long context to be able to learn reasoning, reflection, backtracking, reevaluation, etc. One thing to note is that the DeepSeek R1 models do not use process reward models, which is something that most likely OpenAI's O series models are using, because and yet they have performance which is kind of on par with O1 level performance, which isn't just outcome rewards. Uh, Maybe you can combine the two and get even better. Maybe O1 already does it. Uh, DeepSeek tried it; they weren't very successful, but the final word on that is published open. Now, the major implication of this is that this reduces the need for fine-grained supervised data or fine-grained RL data, right? Reward data. So if you have to collect uh, uh, human preference or scores for every step, that's in a reasoning process, that's costly. Uh, so if you can get by with only outcome rewards and achieve similar performance, that's a good sign for uh, this thread of research. Okay, so with that, let me now talk about open source efforts. Uh, with the release of R1, there has been a lot of effort and a lot of projects have been kickstarted, which are looking to learn from R1 and replicate R1 and delve deeper into reinforcement learning, reasoning, etc. So broadly, the kind of projects can be looked at into two threads. So one is data curation and distillation, where the goal is sort of to take R1 model, generate data with reasoning threads, and then do SFT so as to on smaller models, so as to imbibe them with reasoning capabilities. So this is similar to what DeepSeek has already done with releasing the digital models. There are lots of efforts to replicate that one. The other kind of work is to actually, now that DeepSeek has shown that pure RL works, can that be replicated? And that's another line of work that's going on. So let's go over some of those efforts quickly. So on the data curation and distillation end, there are multiple open source efforts from Bespoke Lab, Open Thoughts, Dolphin, and notably OpenR1, which is an open source project driven by Hugging Face, and they are exploring a lot of things. So most of the efforts on data curation are using the DeepSeek API to generate data. What is notable is OpenR1 has actually tried to host DeepSeek R1 and generate the data, and there are some interesting learnings that they have posted on their blog post. So they sort of said that you might need up to 32 H100s to uh, get a decent throughput, and the average response length of DeepSeek response is around 6,000 tokens. So this on the left hand side, you can see a summary of some of the major datasets already in the public domain, distilled from generated from R1, and of these open thoughts looks like very promising because of the variety of domains it has done. Dolphin is also fairly large, but there's no documentation to sort of tell anything about its quality. OpenR1 math is interesting because this has been generated by running DeepSeek locally. And based on all this data, a bunch of distilled models have already been trained. Uh, uh, the DeepSeek distilled models themselves are fairly strong, and uh, a couple of models from OpenThinker, the Open Thoughts project, uh, are kind of getting close to where their corresponding DeepSeek distilled models are. So interesting times, uh, and there is a lot more to watch in this space. Now, a little more insight into the SFT process for reasoning. Uh, there are a couple of papers out recently, so let's discuss that. So now the question is, uh, if you are fine-tuning a reasoning traces, what kind of reasoning trace should you train on? So should you correct on fine-tune on a reasoning trace that only has the correct response? That means the single chain of correct reasoning that gets you to the answer, or do you train on the entire reasoning trace, which includes correction, verification, backtracking, the model's self-infection, etc. Right? So the first one is what you can call shortcut learning. Just take the most shortest path to the solution. Whereas the second one can be called journey learning, where the reasoning trace sort of looks at all the learning traces during learning, and there are some results to indicate that if you do this kind of journey learning, that's much better for the model to learn reasoning uh, faster. But this is a very initial results. Now, on the role of supervised fine tuning, there's an interesting paper, and this is kind of a summary of that work. Uh, so what this paper looks at is, okay, so should you train on long COT? One of the studies they do is should you train on long chain of thought or short chain of thought? So short chain of thought is what even today's uh, standard instruct models can do. They can also do chain of thought reasoning, so you can generate chain of thought from that, but they typically tend to be short, whereas long chain of thought is what these reasoning models can generate. So now, when you want to distill, which one is better? And here again, the takeaway seems to be that uh, supervised fine tuning with long chain of thought is better than doing it with short chain of thought data. And particularly, like if you are using SFT to initialize RL, then it's better to start with SFT on long chain of thought. And finally, okay, SFT initialization matters for reinforcement learning. So high quality long COT patterns will lead to significantly better generalization RL gains rather than uh, the COTs that are sort of artificial constructed using complex processes. It's better to have natural emergent long COT patterns that come from models like R1. Now, on the reinforcement learning end, there are again some efforts to replicate DeepSeek R1 which is the pure RL model. But of course, as we saw, this needs a really strong base model, large model, and then we do reinforcement learning at that scale. It's I think it'll take a while to get there. People are now starting with smaller models and simple tasks. So, for instance, the team from UCB doing Tiny Zero uh, is reproducing R1 on simple tasks like countdown and multiplication. So, can the model automatically learn this? The key thing being to see is can the uh, reasoning automatically emerge? And their findings indicate that it does on these simple tasks. Similarly, the simple RL reason process also does it on a small math data set, but they also observe interesting training dynamics emerge, right? So that what we saw, right? Self-reflection behavior or the length increasing as the length of the response increasing as the uh, training proceeds, right? Uh, right. So there is improvement over other math models, but it still lags the DeepSeek digital models. So given the small scale at which it is being done, that's now one of the key things with the DeepSeek R1 models is that they use a reinforcement learning algorithm called GRPO, and which is more efficient than PPO. And the Open R1 project from Hugging Face has done an implementation of GRPO and integrated it with its popular TRL library. And there are some initial results on Math 500 which looked promising. But all in all, yeah, this thread is proceeding a little more slowly because it's more complex, it needs more compute, etc. But exciting times. One interesting question is, okay, we saw that the model generates very complex reasoning patterns. You might not be interested in it, and it's just a waste of compute and inference time. So, can we control the model's thinking time? And, during reinforcement learning, this can be achieved by adding a length penalty. Uh, and so, length penalty can be such that if the answer is correct, then shorter responses get more reward. But if the answer is wrong, then you want the model to think more, and so it should get more reward for longer responses. And so with that, it's seen that the model can sort of learn to spend less time thinking on simple tasks like JSON 8K, simpler math tasks compared to INA 2024, which is a more complex math task. And so here you can see that the thinking time is kind of much more than what you would need for uh, uh, like if you had to do full reasoning or if you had calibrated reasoning, the calibrated reasoning would take more thinking tokens compared to smaller tokens. So that's a very interesting approach. More interesting. to say hackish approach is what is called budget forcing. Very interesting. So is there an easier way to basically control the model's thinking time? So what this approach does is very simple. I mean, if you want the model to uh, kind of think longer, then you do some force decoding, and at some point in the model's generation, you insert the weight token, and that sort of signals to the model that okay, now I need to maybe rethink, reevaluate, and think more, and it actually does it. If you look at the DeepSeek R1 outputs, this is very common. It generates these tokens like weight, etc., and then goes on into different tracks of evaluation. So just inserting it into the decoding process at inference time can help the model reason better. Suppose you want to do less reasoning. And if you look at the DeepSeek R1 outputs, you can see that the model actually learns the correct answer fairly early in its reasoning process. Then it goes into verifying the answer, etc. So you don't really want all that, you just want the final answer. So a very simple trick, if you insert a phrase like final answer into the uh, stream and as the model continue generation, the model just generates the final output. So you can wait for some fixed number of tokens and then force decode the model to generate final answer, and that looks to be promising again. Okay. Now, uh, another work which is interesting is one from Perplexity AI. So Perplexity AI has released this model called R1 1776, where the goal is to debias R1. So R1, it is known, DeepSeek R1, it is known, has been trained to censor many topics that are controversial in China. So what Perplexity did is took this R1 model and post-trained it to sort of not censor these topics which are censored, right? And the way they did it is sort of they identified some censored prompts using custom classifier, and then they generate a lot of COT data, and then fine-tune the DeepSeek R1 model in order to get the final R1 1776 model. I'm curious why they have the name 1776. Uh, okay, but if you can see the chart below, you can see that now the China censorship percentage compared to DeepSeek R1, which is like 80 plus percentage censoring Chinese controversial topics, is near zero for R1, as it is for many of the other frontier models. So, uh, so the model has effectively unlearned all the censorship. At the same time, uh, the model is able to retain performance on other benchmarks on par with R1. And on the right hand side, you can see sort of what the model is achieving. So on a question about Uyghurs in China, whereas DeepSeek R1 sort of censors and gives a very kind of plain response, the R1 176 model gives you a different perspective, more detailed response without censorship. So these are exciting times, and there are many more directions to probably explore. So distillation surely is an active area of work, and how do we close the distillation gap with respect to the teachers is interesting. How do you improve the inference efficiency of the distilled models, given that they're generating long tokens? Is interesting. Uh, on the reinforcement learning side, work is very nascent. How do we scale this up to uh, have high quality reinforcement learning at scale? Is interesting. I put in multilingual because that's an area I kind of work on a lot. And so, how do reasoning models work in non-English settings? How do they do multilingual thinking? And we really need multilingual reasoning benchmarks. We don't really have many, so as to drive multilingual reasoning research. So with that, thank you. Uh, that's it about DeepSeek R1.